All right, welcome back to Biostats. This is Module 15A on multiple testing and ANOVA, or analysis of variance. So imagine you're studying a new drug and whether or not it or aspirin, so you've got two possible cures here, treat a particular type of pain after physical therapy. You're going to compare that to a control group, so you've got a placebo pill. As we've discussed in the last chapter, it's important to have controls in experimental studies. Um, and so you're going to compare the control group to the group with the new drug and a group with aspirin. So you've got three groups, and hours free from pain is the response variable. That's a continuous numerical variable. So if you collect the data, should you just conduct three t-tests? Just to be explicit here, the three t-tests would be like control versus the new drug, control versus aspirin, drug versus aspirin. Is that the best way to analyze this data? It seems appropriate since we're looking at a continuous numerical variable, and we've looked at two sample t-tests before. But recall that the significance level alpha is supposed to be the probability of rejecting the null hypothesis even when the null hypothesis is true. So if we do three significant tests, each of them at the significance level of alpha, what's the probability that at least one of them will have a rejection in at least one of them when the null hypothesis is true? So if the null hypothesis is true, we would hope that we'd get zero rejections. But of course, we have to choose a significance level and tolerate some possibility of a type 1 error. Well, this probability would just be 1 minus the probability of zero rejections, right? And if we think about what that probability, how we could calculate that probability, this up here is the same stuff. Probability of one or more rejections is 1 minus the probability of zero rejections. That would be, if we assume that the three tests are independent of each other, which is questionable in this case, that would be 1 minus the probability of do not reject on test 1 times the probability of do not reject on test 2 times the probability of do not reject on test 3. So if we're using alpha for each of those, sorry, I shouldn't have the probabilities here. It should just say 1 minus alpha times 1 minus alpha times 1 minus alpha. Sorry about that. So it's 1 over 1 minus alpha cubed. And so if we're using the standard 5% level, that would be 0.95 cubed. So that is 1 minus about 0.857. So we get a number of 0.143. That's almost 3 times our stated significance level. So once again, what is that? That's the probability that we would reject on at least one of the tests, even though the null hypothesis is true. So we're telling the reader of our paper that we're only going to falsely reject 5% of the time when the null is true, but we're actually falsely rejecting 14.3% of the time. So that's about 3 times as bad as our reported alpha, almost. Our three tests are not independent because we're using the same data for the third test that has already been used in one of the two preceding tests. It turns out that means it's not quite as high as that, but it's tricky to calculate exactly what it would be, but it's still going to be much higher than 0.05. And so hopefully you can see this idea of if we just keep rolling the dice and trying more tests, we're going to falsely reject much higher than our stated alpha. And so that's not what we want in a statistical test. We want to be able to be clear about what our probability of a type 1 error rate is. So note again that it's good experimental design to test multiple treatments at the same time. So that's not the problem. The fact that we're looking at 3 different treatments, a placebo and 2 real treatments, is not the problem. Remember that doing them at the same time prevents confounding of time-dependent effects, so we don't want to do them in series. And the factorial design really encourages us to look for all possible interactions. That's when we're talking about multiple explanatory variables. That's not the case here, but we just want to emphasize that we're frequently encouraging you to do multiple trials at the same time so that you can look for interactions and prevent confounding effects that are associated with the treatments. The problem is I was talking about conducting a series of tests, one after another, and this is called the multiple testing problem, and it requires extra care if we're going to achieve the reported alpha that we're telling our readers about. So we're not going to get in this class, we're not going to get into the depths of how to deal with this multiple testing problem in a generic way, but I do want you to recognize that it is a problem to test multiple times because every time you test, there's a chance of falsely rejecting the null, and so that'll inflate the significance level of the test. So be aware that that's a problem. Okay, So what are we actually going to do instead of doing 3 t-tests? We're going to use something called the analysis of variance, or ANOVA. So we can use ANOVA when we've got k groups, where k is more than 1. It's particularly useful when k is more than 2, because we have a 2-sample t-test when k is exactly 2. It assumes that we have normally distributed response variables, and we're also going to assume equal variance within each group. So we're interested, usually people say when they do an ANOVA, they're interested in testing whether all the means of the groups are equal to each other. And the alternative is just not all of them are equal. So it could be just one of them is different from the others. It could be all of them have different values. Another way of saying that, because we're assuming normality and equal variance, we could say the null hypothesis is that all of our data points come from a single normal with one mean and one standard deviation. The alternative is just rejection of that. And that's a good way to think about it, although frequently people focus on the mean. Okay, so let's go walk through a tiny example, tiny just so we can do the math and it'll make sense, hopefully. Here's the data for that study I talked about. Far too few samples, but here are the data. So we've just got a couple of placebo trials, 4 from the drug and 3 from the aspirin. K is the number of categories, 1, 2, 3 here, okay? So you could visualize that data in this way. Here's the hours free from pain on the y-axis and the 3 groups. Not a lot of data, obviously, but it does look like, even though there's a lot of scatter within each of the groups, it seems like the drug and the aspirin have more hours free of pain than placebo. But is that statistically significant? It's not really obvious because it's such a small sample size and there's so much scatter in this data. So how might we think about summarizing this? Let's just calculate some summary statistics. That's one of our early steps in hypothesis testing. I'm going to use the subscript G for the group just to make it a little bit easier to think about what I'm using here. Your book uses I for the groups, which is certainly common. It's just not quite as intuitive. I mean, there's a lot of indexing in ANOVA. So all the formulas on your equation sheet and in the book are going to use I. But here I'm just using G. Hopefully it'll make sense as we go through. All right, so we can think about the sample size. We actually have different sample sizes in each of our 3 groups, and we'd subscript those by the group numbers. So 2 in the placebo, 4 in the drug, and 3 in the aspirin. N is 9. That's our entire sample size. Notice earlier in the class we were calling capital N the population size, and in ANOVA there's a tendency to call it big N here for the grand sample size. That's a little confusing point because this is not the population size, it's the sample size, but it is a convention in ANOVA to use that capital N there. Okay, so that's just the sample size, not much data there, not much summarizing of the data. And so what are some summary stats we can calculate? Well, we calculate the mean for each group, right? So in the first group, 0 and 1, there's only 2 observations, so that would average to half an hour of pain-free. If you average these 4 values, you get 2.78. If you average these 3 values, you get 3.2. So that's pretty straightforward, hopefully. Those are the group means. So these are a Y bar with a subscript indicating which group it belongs to. So it's not a mean of the entire data set, it's a mean within each group. We can also calculate the mean for the entire data set, 2.41, and that's the mean of all of these values, all 9 of the values. So notice we're not just averaging these 3 group means. You can think about calculating this as a weighted average of those means, weighted by their sample size, or you can think of it as just adding up all of the data points, dividing by 9, and getting 2.41. So that's what's called the grand mean, the mean of all the data points regardless of what group they're in. So that's another summary statistic that we could report. We can visualize those on the data. Here we have the 1, 2, 3 group means, and here's the grand mean in black. And you can tell that there seems to be some variation in the mean across the groups. The lines are not super close to each other. And ANOVA is going to allow us to determine whether or not that's a significant difference. But we can see that this black line is sort of in the middle of all the data points in some sense. It's, there's only a few data points that are lower than it, but some of them are much lower. So this is the grand mean. Once again, not just the average of the 3 group means, but the average of all of the data. Okay, another summary statistic we've talked about in earlier chapters is the standard deviation. We can calculate that within each group. So the standard deviation for a group, this is the same formula that we've seen before the square root of the variance. The only difference is we're just decorating everything with subscripts for the group that is involved here. So a particular value from the group, we're summing over j for all the members of that group, j being the index within the group, of the sample within the group, and then we're subtracting off the mean for that group, squaring that, summing those up, and then dividing by the group sample size by 1. So for instance, if we wanted to calculate the standard deviation for this group, it's 0 minus 1/2, there's our group mean of 1/2, squared, plus 1 minus 1/2 squared. We add up those two things, and the denominator is 2 minus 1, because we have sample size of 2. So we end up with a square root of 1/2 for this, or 0.707. So that's where these numbers are coming from. And those are describing the variability within each of the groups. Not the variability overall, but within each group. Okay, so those are some summary stats that we can calculate. And obviously it's a good idea to give a sense of, get a sense of where our data are falling out. And it's hard to look at the entire table, so the summary stats are going to be a useful way to do that. This is a visualization of those standard deviations that we just calculated. These are from each of the group means, the distance between each point, the deviation between each point and its group mean. So that would be the number squared, and you would add those up and divide by 1 minus the sample size. So we could see that the standard deviation for group 1 is slightly larger than the standard deviation for the other two. The standard deviation for group 2 is the smallest of the three, and you can see this in the figure where these bars, these deviations on average are greater than the deviations in the other groups. Okay, so that's kind of what's being captured in those summary statistics. So let's think a little bit back to chapter 2 or 3 whenever we talked about summary statistics and what is a variance. A variance is kind of like a mean squared deviation. So why do I say it's kind of like a mean? Well, we don't divide by the number of observations, we divide by n minus 1. But this is the formula we saw earlier for the variance. It's the sum of the squared deviations. A squared deviation from the mean is what we mean by that. So every particular value minus the mean, we square that and we sum them up. That's the sum of squared deviations. We divide by something that's close to the number of terms there. And this denominator is chosen using some fancy statistics to guarantee that this is an unbiased estimator of the variance if we had a really large sample size. So it seems a little weird that it's not quite the mean, but don't get too distressed by that. Of course, we give you the formula on the formula sheets. Note that in a bit of confusing terminology, squared deviations show up a lot in statistics, and people often refer to them as just squares. And people often say the sum of squares when they're talking about sum of squared deviations. So it's a little annoying that there's a tendency to be sloppy in the literature, but you'll see this throughout the discussion of ANOVA, is that the general terminology that people use is going to refer to things like sum of squares and mean squares. And it's really these squared deviations, not the data points themselves, that are being squared. Okay, so another reminder, if we were interested in this hypothesis test that two means were equal to each other and we had normally distributed data, you might say, okay, we should be doing a two-sample t-test. How do we do a two-sample t-test? The test statistic, when we're both testing whether both of these are equal to each other, so the difference in one and the other is 0, if that's what we're testing, then this is the numerator of our t-statistic, and the denominator with the standard error, right? So this is actually the formula for the standard error in the Welch's, or excuse me, in our two-sample t-test, assuming the same variance. And there's our numerator, just the difference of variance. If you think sort of on a higher level, abstract level, not just the actual calculations, what are these parts of the t-statistic? The numerator is how much the y's differ from each other, the y bars, how much the means differ. And then in the denominator, we've got this pooled variance, so that's a measure of variability within each group. That's how we calculated that pooled variance. It was an average of the variation within each group taken from both of the groups. And then there's some kind of sample size effect here, right? So that's kind of what's going on a really broad scale. As we move to more than two groups, we can't just calculate a difference, a single difference for three numbers. And so how are we going to encapsulate that? Well, in ANOVA, we're going to calculate something called an F statistic, where the numerator is called the mean squared groups and the denominator is the mean squared error. What the numerator and denominator both are estimates of the variance in the population if the null is true. So this is, if the null hypothesis is true, they'll both be estimating the same variance. And so the top one, much like our t-statistic, this was difference in y bars. The top one's going to be estimating the variance just from the group means, all of the group means that we get. And the bottom, that's going to be within group variances, much like in a two-sample t-test, this pooled variance also came from within group variance measurements. So it's really, in some ways, pretty similar to what we've seen before. It's just ANOVA has a pretty complicated test statistic, and we're going to walk through how to calculate it. It's not quite as intuitive, but I want you to realize that it is, in some senses, quite similar. We're getting two ways to estimate the variance, and if their null hypothesis is true, both of them will be equal to each other. Both those estimates will get close to each other. They won't be exactly equal because of sampling error, but they should be close to equal to each other. So if the null is true, all the data come from the normal. Of course, the within group variance is an estimate of the variance for that group, and if there's only one variance overall, that should be pretty close to the variance, right? So the bottom, the denominator is going to be based on those within group variances. Those should all estimate the population variance. But remember that the numerators is based on the y bars. The y bars for each group are sample means for a group, and under the null hypothesis, the group has a mean of mu, and the variation within the group is sigma. And remember, we have a sampling distribution of the mean way back from chapter 4 that says the means should follow a normal centered around the same mu with a standard deviation of sigma divided by the square root of the sample size. So our theory gives us a sense of how much scatter there should be in the y bars, and how you can imagine sort of estimating this sigma because we know all of the sample sizes. If we can look at the variation within all the y bars, which should give us a hint on how much variation is in the population we're drawing from, because that's a key determinant of the spread of the y bars, right? So that's the idea behind ANOVA. If we see a lot of spread in the y bars and the numerators, that means a large variance. We can compare that variance to what we get from the denominators, which look at the within group variances, okay? And as we get to a really large sample size, really large number of categories, and a large number of groups, we should be able to estimate those variances really well. And if the null is true, then the F statistic is going to get closer and closer to 1 as our sample size and number of groups equals 1. And of course, we're going to have a statistical distribution of the F statistics so that we can actually look at probabilities of various extreme values. Okay, so that's the general idea. I know that's a lot of terminology. We're going to walk through pretty slowly how to calculate this and put all this information in an ANOVA table, and hopefully it'll make more sense then. So here's our data and summary statistics up here. This is the raw data and summary stats. This is the ANOVA table that we work through and fill in as we're doing an ANOVA analysis, and it's important to be able to read and interpret these. Often a common test question is just to give you some of the parts of this table and see if you can fill in the rest without even seeing the data, because there are certain relationships that if you understand how ANOVA works, you should be able to do that. Okay, so I haven't told you yet how ANOVA works in detail, so let's go get to it and see what we do. I'm just going to drop the raw data and focus on the summary stats first. So the next few slides are just going to have these summary stats, but they're not going to change from slide to slide. It's the same data set throughout this lecture. And here's the ANOVA table that we're going to fill in each time. Okay, so the first column, I should have paused here and just emphasized it. The first column was sum of squares, the first column after our source of information. And this fourth column is the mean squares here. I'm going to abbreviate those SS and MS for mean squares. So sum of squares, once again, as I hinted at before, the sum of squares is going to be a sum of squared deviations from the mean. So the sum of squared groups, we break in ANOVA, we break out things that are going to be referring to groups and things that refer to error within each group, and we just call that an error term. So this is between groups, between and within. There's a tradition to call them groups and error, which is a bit confusing, I admit, but what can we do? All right, so SS groups, how do we calculate the sum of squared groups? It's a sum of squared deviations, and it's actually weighted by the size of the group, so it's kind of a weighted sum. What are these deviations we're looking at? These squared deviations. We do square each term here. It's the group mean minus the grand mean. So this is what's going to be in the denominator, and is going to lead to the numerator of our F statistic. And I mentioned that was calculated by looking at variation within means. And so notice that the raw data don't show up here. It's just the sample statistics, the sample means for each of the groups. So it's how much each group is deviating from the grand mean of the data. And then that's weighted by the sample size, as I mentioned. So for instance, if we were going to calculate the sum of squared groups for this tiny data set, we have 0.5 is the mean for the placebo, 2.41 is the grand mean. That's going to show up in each of these terms. So we're going to get that deviation and square it, and we're going to weight that by the sample size of that group. The sample size for group 1 was 2. The next term in the summation is 2.78, this mean, minus the same grand mean squared, and the weighting term is 4. And then the final one, we have a mean of 3.2 for the aspirin group, same grand mean, and 3 samples from that group. Okay, so if you were to plug this into your calculator and chug through here, you'd get this 9.701. So that's a sum of squared groups. It's not a variance because we haven't divided through by anything, and it's kind of a weird weighted sum, but it's encapsulating how much variability there is in the group means from the grand mean. So if the null hypothesis is true, this number tends to be pretty small because each of the groups is going to have a number pretty close to the grand mean. Okay, so that's capturing how much variability there is group to group. Okay, what about this degrees of freedom? There's actually 2 degrees of freedom in ANOVA, one for groups and one for errors. The degrees of freedom for groups it's very similar to how we were thinking about degrees of freedom before when we were estimating variances. It's the number of data points minus 1, but here in this formula, we're doing a summation for each of the groups, so it's going group 1 up to k. So that becomes our sort of sample size in the SS groups calculation, is how many categories are there, how many groups are there. So it's k minus 1, it's not n minus 1. So we have 3 categories. We lose a degree of freedom because we're estimating the variance from the data, so we only have 2 degrees of freedom. So there's our degree of freedom of 2 for the groups. Okay, that's our group's degree of freedom. All right, how do we get the sum of squares for the error? Oh, sorry, the mean, sorry, I got ahead of myself. The mean squares for the groups is, remember the sum of squared groups divided by something like the sample size in order for estimating the variance. So this is kind of like the n minus 1 factor that goes in the bottom of a variance. Now it's a k minus 1 that's in the denominator of a variance calculated. So this mean squared groups is a kind of variance estimate. It's a weird variance estimate, but it's encapsulating the variance by summing up the squared deviations in the groups and dividing by the degrees of freedoms of the groups. And so that gives us an estimate that is an unbiased estimate of the variance if the null hypothesis is true, of 4.851 hours. So that's how we fill out this first part of the table. Now we can do the error portion. How do we calculate the sum of squared errors? It's similar, once again, to the numerator of a variance calculation. We're going to be summing for all of the categories. We're summing up the variance within that group. So that is the standard deviation squared. We calculated standard deviations before. We're going to square those. And once again, we're going to weight them. But this time, we've lost a degree of freedom in estimating each one of these standard deviations. So it's the group size minus 1 in each case. So it's these variances, these standard deviations that we calculated before are going to show up here, and we're losing a sample size. So instead of 2, 4, 3, we have 1, 3, 2 for our coefficients here. So we plug that in. This is very similar to calculating a pooled variance in some sense, the part of the pooled variance, the numerator part of the pooled variance. And we get 1.947 for that sum of squared errors. And so this is not picking up any differences in the means between the groups. It's just looking at scatter within each group. Okay. Um, so this doesn't really tell us anything about by itself about whether the null is wrong. It just sort of gives us a sense of how much variability there is. It's not a variance yet because it's just the sum of squared. But once again, we can calculate a degree of freedom. Now the degree of freedom is going to be the grand sample size minus the number of categories. And so that's because we lose a degree of freedom for each category, so that's why we're subtracting k instead of subtracting 1. So 9 is our total sample size. We lost 3 degrees of freedom, so we're down to 6 here for our error degrees of freedom. Okay, and then once again, we can calculate a mean square, and now it's going to be the mean squared error instead of the mean squared group, and it's calculated in just an analogous way. The mean squared error is the sum of squared errors divided by the degrees of freedom of the error term, right? So 1.957 divided by 6 gives us 0.325. So in the mean squared column, it's always going to be this is the numerator and this is the denominator, and that gives you that mean squared column. So this is the point I was making earlier, that we can calculate many things from the table if we have some of the information but not all of the information. Okay, so we get a lower mean squared number here, 0.325. Okay, another thing that we can do is total up this total sum of variation. It turns out variances in many contexts are additive, and these sum of squared terms are useful. We're going to see that later. So the sum of squared total here is just the sum of the groups term and the error term. So that's 11.649. But it's also actually the same thing as if we had calculated the squared deviations of each data point from the grand mean. So that's a tricky proof, but it is this is sort of like the numerator in the variance in calculation if we had just looked at the data in one big group instead of 3 separate groups. It's usually easier to calculate it this way by summing up the SS groups and the SS errors. And the degree of freedom total is just the sum of those 2 degrees of freedom. That turns out to be n minus 1 all the time. So 2 plus 6 is 8, so remember our sample size was 9, so we have a DF total of 8. We don't actually use this a whole lot, but you can check yourself that degree of freedom is just 1 minus the sample size, the total sample size. Okay. Now, how do we calculate our test statistics? So what I mentioned to you, and we can't prove in this class because it just involves a lot of math, but both of these mean squared terms will be equal to each other, or they're both estimates of the variance in the population if the null hypothesis is true. They're not biased estimates if the null hypothesis is false, but if the null hypothesis is true, they should be equal to each other, or pretty close to equal to each other given sampling error. So what we can do is calculate a ratio of those two things. So the idea is we're going to put the group variation between group variation above the estimate from between group variation above the estimate from within group variation. In this case, we get 14.94. If the null hypothesis were true, we'd expect numbers somewhere around 1. So we can see this is a pretty large value, and it makes us maybe doubt whether or not the null hypothesis is true. So that's our test statistic. It takes a lot to calculate a test statistic of ANOVA. So we've finally gotten the test statistic. Now we want to calculate the p-value to determine whether or not we reject the null. So once again, in order to calculate a p-value, we compare it to the null distribution of the test statistic. So this is the null distribution of an F distribution with 2 degrees of freedom in the numerator and 6 degrees of freedom in the denominator. So the F distribution, once again, like the chi-square, it's a family of distributions, but now there's actually 2 dimensions to it, kind of like the Mann-Whitney U-test. There's 2 degrees of freedom, one for the numerator and the second for the denominator. And you do have to distinguish between them. They're not reversible. The Mann-Whitney table was reversible. That's not going to be the case for the F-test. So we have a numerator degree of freedom and a denominator degree of freedom. So the groups is in the numerator, so we call that the numerator degree of freedom. The error term is in the denominator, so that's the denominator degree of freedom. Okay, so there's the curve. I just put in 1 here as a black line to give a sense of what we'd expect if the null were true. And we see our value here is really extreme we can't even see any area under this curve. The probability looks really, really tiny here, so we're probably going to get a very small p-value. In the F distribution, much like the chi-square, we're only calculating probabilities in the rightward direction. Only large values make us doubt that the null is true. And so we don't do a two-tailed things. We just look at one tail of the distribution. Okay, so we can get that p-value from a table, or using R. As I mentioned, we have to keep track of the numerator degrees of freedom and the denominator degrees of freedom. Here's how to do it in R. I just put in that PF for the probability from the F distribution of the test statistic, 2 degrees of freedom, 6 degrees of freedom, and I asked it to give me not the lower tail, but the upper tail. And that's the answer there. It's this very small number. So our p-value is right around 0.047. Of course, you don't have R on the exam, so how do we read this from a table? Sorry, I should have explained this before, but I should have had this slide maybe a little bit before, but this is just a demonstration that the shape of the F distribution depends quite a bit on these degrees of freedom. So it's really important that we pay attention to both of them and also distinguish between them. And so when the degrees of freedom are really small, df of 1 and d2 of 1, this would be like comparing two groups. Remember the numerator degree of freedom is the number of groups minus 1. So if we see a numerator degree of freedom of 1, that means that the number of groups must have been 2, and we subtracted 1 to get 1. And then this is n minus k for the df2. And so if we have two groups and n minus k equals 1, then we must have only had 3 data points. So that's a tiny, tiny data set, right? 2 groups and 3 total samples. Obviously, you're not going to get a very good estimate of the variance from such a small data set, either between groups or within groups. And so you get this really extreme F distribution that really flattens out, but is actually not that close to 0. And so this it takes a really extreme value in order for us to say, oh, you know what, this is more variation than we'd expect by chance. So these are all null distributions. These are all assuming the null hypothesis is true. But there's a lot of slop if you have really small, either of the degrees of freedom is really small, you're going to have a lot of slop in your F statistic because it's possible to estimate one of those values way off. If we get really large number of categories and a large number of samples, then as we said before, we tend to get pretty good estimates of both of the variances, and so the F statistic is not far off from 1 in those cases. Okay, so the null distribution, changes shape quite a bit for the F. It's a little bit counterintuitive and hard to describe what it looks like, but you should know that as you get to really large numbers, it's going to get tighter and tighter around 1, because that's the expectation under the null, and large sample sizes mean we can estimate it well. Okay, so how do we actually read the number from the table? There's like the Mann-Whitney U, there are multiple tables, one for 0.05 and one for 0.01. We had a numerator degree of freedom of 2 and a denominator degree of freedom of 6. So our critical value is 5.14 for this test. So I didn't show the 0.01 level, but if we actually did the same procedure on the alpha of 0.01 table, this is alpha here, we get 10.92 there. So the critical value at the 0.01 level is 10.92. Our F statistic was 14.94. So our F statistic is greater than the critical value at the 0.01 level. And so that means our p-value is less than that. Remember, we're further out in the tails. The distribution is kind of shaped like that, and 14, or I guess the distribution actually in this case is kind of L-shaped. Doesn't really matter for our purposes because 14 is way out here in the tail, and there's a tiny, tiny probability. Okay, and so our p-value is less than 1%. So one other thing to note here is because only the right side of the tail matters, we'll often denote that with just one tail to indicate from the F distribution, we're only looking at one tail of the distribution. We haven't done like a one-sided test. We're going to reject the null no matter how the groups vary in their means, but this is referring to how many tails of the test statistic contribute to the p-value. So anyway, at this point, we could say that p-value is less than 0.01, which is less than our alpha of 0.05 as our traditional alpha, so we would reject the null hypothesis. And we might summarize that as in a study comparing 3 pain treatments, a placebo, drug, and an aspirin, there's sufficient evidence to reject the null hypothesis that the 3 treatments give equal numbers of hours free of pain. We give our F statistic. It's pretty common to use the degrees of freedom in the subscript there. There's our F statistic. We say the p-value is less than 0.01. That's all we could say if we were using the tables. We could be more specific if we were using R. And then our conclusion is at least one of the means for placebo, drug, or aspirin differs from the others. And then we have lots of summary statistics. It's tedious to report that. And in fact, a lot of people just rely on an ANOVA table to report the summary stats. So you can infer the summary stats from the table as well. Hopefully that makes sense. Another thing you commonly see in ANOVA, and the reason we actually calculated the sum of squares total, is we can look at how much of the variability is explained by the groups. So the sum of squared groups over the sum of squared totals. Remember, the sum of squared groups is how much the group means vary from the grand mean. And so if the group identity is really important to knowing what the value is going to be, then you're going to have a really large number, and it's going to be a large proportion of the total variation. So in this case, it was 0.833. And so that means that approximately 83% of the variability among subjects in the different hours, in terms of hours of pain relief, is explained by the different treatments. So if you know the treatment that an individual was in, you can make a much better guess about what their hours of pain relief is going to be, and the remaining 17% is the error variability, the variation around each of the groups. So just to visualize this a little better, we can go back to the original data. There it is with all its variability. There it is with the group means and the grand mean. This is the sum visualization of the sum of the squares groups. It's only showing the deviations, not the square deviations, because it's hard to depict on a figure. But for each of the groups, each of the members of the groups, what we would add up would be the square deviation here, and this square deviation is the deviation between, say, the mean in group 1 minus the overall grand mean. So this black bar is the grand mean. And so that's what the SS groups is depicting, right? And so if there's a lot of variability in the group means, then this is going to be a big term because the groups seem to be important in explaining the data. This is the SS errors depictions, and once again they would have to be squared to actually be the deviations we're interested in, but they show the deviations within each group, and you can see that there's not a whole lot of variation within each of these groups, right? It's smaller bars than on the previous graph, and that's why in this analysis the group membership meant a lot. You explained a lot by knowing whether or not you were in placebo, drug, or aspirin group because the means were so different from each other. Okay, and then there's the total variation. The total variation, once again, is the sum of the two, the sum of squares groups and sum of squares error, but you can also think of it as the sum squared deviation of each data point from the grand mean, and you can calculate the sum of SS total that way too. And so it's basically the proportion of these deviations that's explained by the groups, and it turns out to be quite a bit of that variation, 83.3%. So you'll frequently see R squared when you have a significant ANOVA result. And you say, okay, we've rejected the null hypothesis. Maybe it's a very subtle effect and we just had a large sample size. Let's convey to the user how much of the variation is explained by the group status. And if that's a large number, then you're saying these groups are really significant in terms of explaining the data. All right, I hope that makes sense, and we'll talk a little bit more about ANOVA and two-way ANOVA in the next lecture.